So it's a pleasure to introduce Cédric Bernardin. He is now professor at the University of Nice, and he will talk about boundary-driven lattice gas with long jumps. Please, Cédric.
Okay, thank you very much. Thank you very much for the invitation. So I have to correct something. Now, University of Nice doesn't exist. It is Université Côte d'Azur, French Riviera University. So I will present some results which have been obtained in collaboration with with Patricia and also some PhD student of Patricia, Pedro Cardoso and Stefano Scotta, and also Byron Jimenez, who is now in Costa Rica. So okay, let me start with some motivation for this work, a general motivation, which is a long-term motivation. I think I was talking of that at IMPA maybe 5-6 years ago with Milton, with Claudio. And so what is the motivation? So it is related to what is called the macroscopic fluctuations theory. So macroscopic fluctuations theory is something which has been probably the main achievement in non-equivalent statistical mechanics since during the last 20 years. And so in a nutshell, what is the problem? So when you have a system of interacting particle system, very large interacting particle system, and so you have to distinguish two kind of situation: when the system is at equilibrium, and when the system is outside of equilibrium. So the meaning of equilibrium is different for physicists and for mathematicians. So when I'm talking about equilibrium, it doesn't mean stationary. So equilibrium means that, for example, if you consider some system which is in contact with two heat baths at two different temperatures, TA and TB, then if the temperatures are the same, then you don't have any current of heat or of energy inside the system. So you have a vanishing current. So it means that you are at equilibrium. And then in this case, if you want to compute the stationary state of this system, so the stationary state is provided by the framework of Gibbs ensemble. So you know that the stationary state is given by the usual formula, exponential of minus h, say h is Hamiltonian divided by the temperature T, which is the temperature of the bath. Now, if the system is outside of equilibrium, the temperature are different, then in principle, usually you don't have any information about the stationary state, which is in this case called non-equilibrium stationary state, because you have some current inside, which is non-vanishing. And then what the problem is, so since you don't have any some formula to compute this non-equilibrium stationary state, and if you want to study some thermodynamical quantities in this non-equilibrium stationary state, so you want to have some information. And during the last 20 years, there have been developed some theory, which is called the macroscopic fluctuations theory, which has been developed mainly by what Derrida called the Italian group, with in particular Claudio inside the Italian group, and also by Derrida himself with some different approach. But so the macroscopic fluctuation theory is some theory which permits to define, for example, the notion of non-equilibrium free energy for systems which are outside of equilibrium. And so now the main motivation of his works that I would present is to try to develop some equivalent macroscopic fluctuation theory in the case where you don't have some diffusive system. It means that the system is described macroscopically by some heat equation, diffusion equation, but it's described by some super-diffusive process, which in my case will be some fractional Laplace. And so the general long-term motivation is to try to develop some macroscopic fluctuation theory in this case, where the bulk system is described by some fractional diffusion equation. To do that, we will study some particular system, probably the simplest system that we could imagine, interacting particle system, very famous one, which is some exclusion process, but with long jumps. Let me introduce the model that I will discuss. So we have some lattice, and so the system is confined to some lattice of size n. So the sides are 1, 2, 3, n minus 1, and you have, so it is a lattice which is here. And now you assume that you have some particle on the lattice, and particles can jump from side to side. And they can jump from side to side with some probability distribution, which is given by phase P of Z, which has some heavy tails. So here, gamma is a parameter, which is positive parameter. So, and you can observe that if gamma is bigger than 2, then in this case, the variance of P is finite, but if gamma is less than 2, the variance is not finite. And so what is the exclusion process? So probably everybody knows, but it is a system in which you have particles which are performing some random walks with this probability transition in continuous time. So they wait for some exponential time. After this exponential time, they try to jump to some site. But what happens is that since there is some exclusion, if the site is occupied by some particles, then the jump is suppressed. So it is here, for example, you have this particle here. We try to jump to this guy. It is empty, so it is okay. But if the particle which is here was trying to jump to this side, then the jumps would be suppressed. And we attached this system with two reservoirs of particles, which will fix the density at the boundaries. Like in the previous picture, in which you had some different temperatures, here you have different densities in the system. And so you need some description of the reservoirs, and there are different possibilities. So here, what we adopt as a reservoir is the following. We assume that so if you are to the right of the site n-1, you can imagine that you have some infinite number of particles on each side, and in the same on the left of the 0. And so the particles now are injected inside of the system with some rate, and this rate depends on several parameters. They can be injected everywhere. So it means that these reservoirs are long jumps also. And we will see later that we can also consider some short range reservoirs without modifying so much the picture. So you have some density on the left, which is rho L, and some density on the right, which is rho R, which is fixed. And we assume that the reservoirs have some intensity, which is regulated by two parameters, kappa, which is just a positive constant, and theta, which can be some number negative or positive. So it means that if theta is positive, and say theta strictly positive, then the reservoir has a weak interaction with the system, while if theta is strictly positive, they have a strong interaction with the system. And if theta equal to 0, they have just some normal intensity of order 1. So the system is a Markov jump process, and it is a Markov jump process with state space which is 0, 1 for lambda m. So I'm just looking at the system inside of the bulk. So the reservoirs are just outside of the system of interest. So, and I denote eta tx equal to 0 means that you don't have particle on the site x. Eta tx equal to 1 means that the site is occupied, and because of the exclusion, you can only have at most one particle per site. And I will denote, so I am mainly interested in the stationary state of the system. So if you wait for a long time, the system is a Markov chain on some finite space. You will reach some stationary state, and this stationary state is non-equilibrium if rho L is different from rho R, so that you have some current of particles crossing the system. And in the case where rho L is equal to rho R, then the system is at equilibrium, and the stationary state is just given by the Bernoulli product measure with density equal to the density of the reservoirs. So this case corresponds to the equilibrium case, and the case where rho L is different from rho R correspond to the non-equilibrium situation. Okay, so I hope that the system is clear. So you have these reservoirs. Reservoirs can inject particles inside, everywhere, in fact, but they try to fix the temperature on the left to be rho L and the temperature on the right to be rho R. But this intensity of the reservoirs is regulated by this parameter kappa and theta. Okay, now let me go to the questions that we would like to answer. So the first question is about hydrodynamic limits. So we know that the number of particles, if you ignore the presence of the reservoirs, the number of particles inside of the system is preserved. And so we want to understand how the density of particles evolve macroscopically. So for that, we introduce this empirical density. And this empirical density, which is just some measure in the macroscopic scale. So macroscopic scale means that U is here in 0, 1. And we just put some eta tx here, which is one particle, 1 or 0, depending if there is a particle at time t on site x. And here it is just a Dirac mass on x over n. And we divide by the volume. So the hydrodynamic limit problem is the following, so that you know probably. So in the time scale t and a, so it means that a is a positive number. So we will study the system as n goes to infinity. So we look at the system in a very long time scale, which depend on this parameter a, and we ask if you assume that initially your empirical density is converging to some initial profile rho 0, which is some, say, which has a density with respect to the Lebesgue measure, so rho 0 u du. So it means that you have some macroscopic profile given by this density profile rho 0. So the question is, does this property propagate with time in this time scale? And then what is the profile that you obtain at time t? What is the PDE that is satisfied by this rho t? So if it is the hydrodynamic limits problem, which is probably the first step if you want to develop some macroscopic fluctuation theory in this context. Okay. And okay, there is some other problem, which is a hydrostatic limit problem. So it means that now you look at the non-equilibrium stationary state. So it means that you look at some infinite time. Okay, you are not in this time scale Tn for a, t equal to infinity. So the system will reach some stationary state, non-equilibrium stationary state, because the densities are different. And then we ask if I'm looking at the density inside the system. So it means that I'm looking at eta x. No. Okay, I'm looking at eta x in the stationary state, the average, and so we expect that in the large size limit, this guy will be close to some macroscopic profile rho bar, but depending on some macroscopic variable x over n. And so, what is the equation which is satisfied by rho bar? This is the question. Okay, so it is hydrostatic because you are not looking at the time evolution of the system. You are looking directly at the system when it is at infinite time. And now the last question is the dynamical large deviation problem and the macroscopic fluctuation theory, which is the following. So it is so macroscopic fluctuation theory is based on some large deviations theory. So so you know that in this, so imagine that you can prove that you have some hydrodynamic limits. So you have a typical profile which appears in this time scale Tn power A. And now the question that you can ask is what is the probability to observe a density, empirical density at time Tna, so in this time scale, large time scale, which is given by some profile pi hat. So it is pi hat, it is just some different profile, which is not the typical profile provided by the hydrodynamic limits. So the profile provided by the hydrodynamic limits is denoted by ρt. And so if you have this probability, you expect that you have some large deviation problem. And so you will have this probability which is will be exponentially small in the size of the system, with some rate function will depend on the profile that you want to observe in these large fluctuations. And this rate function, of course, will satisfy this property that it is equal to 0 on the typical profile. Okay, so that is the probability to see this profile is 1. But if you want to see some other profile in this time scale, it will be exponentially small in the system size and with some rate which is provided by the rate function. Okay, that is the dynamical large deviation problem, because you are looking at the empirical density in some time scale. Now we can formulate the same problem, but in the stationary regime, in the non-equilibrium stationary state. So here I am I'm computing the same large deviation problem, but in the NESS, in the non-equilibrium stationary state. So I have this empirical measure. I'm looking at the system starting in this non-equilibrium stationary state. So in this non-equilibrium stationary state, the typical profile is provided by this hydrostatic profile rho bar, and you want to see what is the probability to see some profile which is different from this rho bar. Again, it will be exponentially small, and it will be exponentially small with some rate of function f of pi. And this f of pi, of course, will vanish on the typical profile rho bar, this hydrostatic profile. So f of rho bar would be equal to 0. And so the question, it is the interest of macroscopic fluctuations theory from the point of view of non-equilibrium statistical mechanics, is that it provides some definition of the free energy for non-equilibrium stationary state when you are outside of the framework of Gibbs ensemble. So now, what is the connection between these two large deviation problems? In fact, so if you know what is a Freund-Wenzel theory, the macroscopic fluctuation theory, in some sense, is just some generalization in infinite dimension of the classical Freund-Wenzel theory, which relate this rate function from the stationary state to the rate functional for the large deviation to observe some trajectory in your dynamical system, which is perturbed. And so what is the claim of the macroscopic fluctuation theory is that this non-equilibrium fluctuation, so non-equilibrium free energy f of pi can be deduced from this rate functional, dynamical rate functional for the hydrodynamic limits by some variational problem. So this variational problem is that you have to take the infimum over all the paths which start at time minus infinity from the stationary profile, and which arrive at time 0 to some given profile pi. And if you take this rate functional here that you evaluate between minus infinity and 0, so it is a functional will depend on all the paths during the time going from minus infinity 0. You minimize this functional over all the paths starting from rho bar, the stationary profile, and finishing at time 0 with pi. Then you will get this f of pi. Okay, and this theory has been developed for, as I said before, diffusive systems, also developed for systems which are described by conservation laws in in one dimension and for mainly for one conserved quantities. There are few results with several conserved quantities, and this variational problem. So it is a general framework. Afterwards, you see, it is quite difficult to solve this infinite dimensional problem. And so, in fact, this problem here to derive this large deviation functional, this dynamical large deviation problem is easier than to derive this problem here. But with the macroscopic fluctuation theory, you have this connection which is provided here. And so if you are able to derive this rate functional, a priori you have some formula for the non-equivalent free energy. And so now the long-term project is to develop some similar theory for systems which are not diffusive, but which are described by fractional equation. So we are still very far from to be able to say something about this macroscopic fluctuation theory. And so the result I would like to present are just the first step in this program, which is the derivation of hydrodynamic limits. Okay, so I come back to this problem with a boundary-driven long jumps symmetric exclusion process. So I will not consider asymmetric system. It is also some other things which is of interest. And so let me start with the theorem that that we proved with Patricia, with Pedro Cardoso, with Byron and Stefano Scotta. So here, I present just a theorem in some picture. So I recall you that you have in this system with this boundary-driven long jumps exclusion process. So at the boundaries, you have some reservoirs, and the intensity of these reservoirs are regulated by kappa divided by n power theta. Okay, so this theta is some important parameter which say what is the intensity of this the strength of these reservoirs on the bulk system. And the other parameter was gamma, and this gamma was in the jump probability transition. Pz was some constant divided by z power 1 plus gamma. So I recall that if gamma is bigger than 2, we are in one dimension, then you have a finite variance for p. But when gamma is less than 2, it is some infinite variance. Okay, so I think that the first time that this system was considered, at least in the mathematical literature, was in some paper by Milton. I don't know if this paper has been published at the end, but it is at least on archive. And but it was without the boundaries. And what Milton proved is that if you consider this system, then the hydrodynamic limits are provided by some fractional diffusion equation. But so in the work of Milton, it was without any boundaries. It was on the infinite line. Okay, and then we decided to look at the system in the case where you have some contact, some boundaries. So it means that you have some contact with some reservoirs of particles with different densities at the boundaries. And so what we have some complete picture of for this system. What we obtain is that the hydrodynamic limits are given by some PDEs, which are the following. So it is dt of rho t equal to some operator of rho t plus some boundary conditions, which depends on this parameter gamma and theta. Okay, so let me comment a bit this picture. So let us start with the case where gamma is bigger than 2. So it is here. So gamma bigger than 2 means that P has some finite variance. So the system is very close to a system with nearest neighbor interactions. And the system with nearest neighbor interaction was considered by Cardoso and some other co-authors a few years ago in the nearest neighbor case. And they prove in many this picture, which is the blue-violet picture, that where you have some transition between some boundary conditions. So if you, okay, here, imagine here, so theta equal to 0 means that the reservoirs of intensity 1. So if you have this theta equal to 0, so it is quite the usual picture, what you have is just some diffusion equation, some heat equation as hydrodynamic limits with Dirichlet boundary condition. Now, if you increase the theta, it means that you are decreasing the intensity of the reservoirs. Then you can imagine that when theta is very large, you will get some Neumann boundary conditions, because it is like if the reservoirs were not existing. And this is true if theta, in fact, is strictly bigger than 1. While if theta equal to 1, you have some special regime, which is some interpolation between this diffusion with Dirichlet boundary condition and this diffusion with Neumann boundary conditions. In this case, what you get when theta equal to 1, when the intensity of these reservoirs are order kappa over n, is that you have some diffusion with Robin boundary conditions. So Robin boundary conditions is something which is expressing the fact that this is a relation between the flux at the boundaries and the density at the boundary. Okay, now, this is quite, in some sense, more standard. Now it is this picture. Okay, I don't comment so much about the case theta negative. Theta negative means that the reservoir are very intense. And so it means that you are injecting a lot of particles inside the system. So it is like if you were just injecting particle and the particle don't have time to move inside the system, so that you have just some reaction equation. So, but let us look at this green zone. So in the green zone, what we were able to establish is that you have also some transition between different equation. But before, for gamma bigger than 2, it was provided by diffusion equation. Now the hydrodynamic limits are provided by fractional diffusion equation. So it means that you are replacing the Laplacian by a fractional Laplacian. So power of the Laplacian, and you have to inject some boundary condition. And so we have a natural prolongation of this line, which was here. So here it was for theta equal to 1. Now the transition is for theta equal gamma minus 1. For theta equal gamma minus 1, for this intensity of the reservoirs, you have a fractional diffusion equation with Robin boundary condition. Of course, I have to precise what are Robin boundary conditions in this fractional case. And if theta is bigger than gamma minus 1, you have some fractional diffusion equation with Neumann boundary condition. While if theta is less than gamma minus 1, you have some fractional diffusion equation with Dirichlet boundary condition. If theta equal to 0, it is a bit different. You have Dirichlet boundary condition plus some reaction term. So it is a general picture. I don't want to write all these equations because it is a bit boring. But I will just comment a bit about this equation in some case, in the case where theta equal gamma minus 1 on this line. Okay, I will not give all the definition of the equations. Yes, something else is that in fact you can perform the same analysis in the case where you replace these reservoirs, which are infinitely extended to the left and to the right, to some more classical, maybe, reservoir in which you inject particles only at the the nearest neighbor sites of the point 0 and 1. But and then you don't get some very different picture, in fact. Okay. So just give me some graphs of the okay, here it is a graph of the hydrostatic profile, but in fact some similar graphs could be obtained for the hydrodynamic profiles. And what you observe, so it depends on depends on the parameters, but here there are many for gamma equal gamma between less than 2. And what you observe is that at the boundaries, you have some singularity of the profile. The profile is not differentiable at the boundary. In the nearest neighbor case, what you get is just some linear profile between rho L and rho R. But in the case where gamma is less than 2, you have some fractional Laplacian with boundary conditions, and the hydrostatic profile, for example, is becomes singular here, so it is not differentiable. And in fact, it is something which is even in the PD's literatures. Okay, we asked to some people working in analysis, and they don't know how to get the regularity of his profile. So this is some interesting question from the point of view of PDs, but it doesn't seem to be so easy. At least the people we asked, they didn't know easily how to reply to the question. But this singularity is also explain why we will have some problems to derive hydrodynamic limits close to the boundaries. The real problem is the boundaries. For the system is not the bulk, because the system, as we will see, will have some linear equations bulk, but at the boundaries, you have to precise what are the boundary conditions, and if these boundary conditions will be will involve some profiles which are not differentiable. Also, okay, I told you that in fact these equations, these hydrodynamic limits, were given by fractional diffusion equation with boundary conditions. But in fact, when you think about this claim, there is something which is not clear, because what is a fractional Laplacian on a bounded domain on 0, 1? There are several different definitions that you can find in the PD's literature. So I just give a few ones. So first, I recall you what is the fractional Laplacian in the infinite domain. So it is just the easiest way is to define it by in Fourier space. It is just inside to put to take the square of the Fourier mode. You take a power gamma of the Fourier mode. So, and then because okay, it is local in Fourier space. This operator is local in Fourier space. But when you rewrite it in the physical space, but then it becomes some non-local operator. So it means that if you want to compute the value of his fractional Laplacian at the point U, you need to know the value of the function everywhere in the space. So it is a non-local operator. And so you can imagine that if you want to describe some fractional equation, fractional diffusion equation with boundary conditions, there is something which is a bit competitive, because fractional Laplacian is non-local operator, while boundary conditions a priori are local conditions. And so you can imagine that the fractional Laplacian which will appear in these hydrodynamic limits could be, for example, this regional fractional Laplacian. Restricted fractional Laplacian. So I give here the definition. It's just that you extend your function by 0 outside of 0, 1, and you just take the same definition of the usual fractional Laplacian, but with just the extension 0 outside. This is the first way to do it. The second one is a regional fractional Laplacian, which will appear in the cycle, where in fact you restrict this interval, which was defined on R, you are restricted to the domains that you are considering, which is here 0, 1. It is a second possibility, and there are also some spectral fractional Laplacians. where what you do is that you take some basis, orthogonal basis of the Laplacian on the domain 0, 1. So when I say basis, you have many bases depending on the boundary conditions that you are putting for lambda on the domain, and then you define it similar to what we have here in the infinite volume by Fourier transform, but with his autonomous basis. So it is 3 different ways to define fractional Laplacians, and a priori you could imagine that these fractional Laplacian could appear as in the hydrodynamic limits. It turns out that in our study, what we obtain is that this is a regional fractional Laplacian, which is really the object which is describing the system. Okay, so now let me describe a bit the kind of equations that we got, the hydrodynamic limits. So I'm just considering the case where, so I'm considering the case where gamma is between 1 and 2. So you have infinite variance, you will have some fractional Laplacian, and theta equal to gamma minus 1. So it was the line in the graph where you have some Robin's boundary conditions, fractional Robin's boundary conditions. So as it is usual in hydrodynamic limits theory, in order to derive these hydrodynamic limits, what we do is that you show that the empirical density are tight, and then so you try to characterize the limiting points by showing that they are satisfying some weak formulation of the PDEs that you want to derive. And if you have uniqueness of the PDEs, which is that you expect to be the hydrodynamic limit, then the limiting points are unique, and then you know that the sequence is converging to this limiting point. So you have to find some weak formulation of the hydrodynamic equations that you are interested in. So for example, in this case, in fractional diffusion equation with Robin's boundary condition, this is the weak formulation. So first you have to give some space, some Sobolev space in which are living the solution. So here it is just given by some fractional Sobolev space, which implies in particular that the hydrodynamic profile will be continuous, but you will not have some differentiable profiles at the boundary. Why it is in the bulk, and you have to find some weak formulation of the PDE that you're interested in, and show that you have uniqueness of this weak formulation. That you have uniqueness of the solution of the PDE when it is expressed with this weak formulation. So here in this case, it is that for every test function g, depending on time and space, so u is in 0, 1, you have this equation which is written here, and you see in fact the boundary conditions are encapsulated in 2 places here in this term, but also in this space of test function. So depending on the space of test function that you are taking, it's not so clear a priori when you try to write the weak formulation which kind of test function you have to choose. Okay, so but anyway, after working, you understand that in this case, for example, you have to take this test function, and you have some boundary conditions which are expressed here in this term. So kappa, I recall you that it is a term, the boundaries, the reservoirs are for the kappa divided by n power theta. So kappa is this parameter, and this m is this guy where it is a sum of z bigger than 1. So p is symmetric, so it is a number which is finite. Okay, here it is in the case gamma between 1 and 2. And okay, I will not give the proof of the derivation of this weak formulation, but the main difficulty is not to obtain these terms which are here, because in fact, as you can see, it is weak formulation of a linear equation. And the real difficulty is to obtain this guy. And to obtain this guy, you have to perform some replacement lemma at the boundaries of the system. And since you have, these replacement lemmas are what is called moving particle lemma. Since you have long jumps, you have to do some special things in order to derive these replacement lemma at the boundary to show that the density at the occupation variable at site 0, for example, is close to the empirical density in a box of size epsilon n around 0, where epsilon goes to 0 and n goes to infinity. And and even if it is a linear equation with some boundary condition, I have to say that we don't have explicit solution of his linear equations. So and in particular, we don't know the regularity at the boundary of his hydrodynamic profile. So it is a question that I mentioned before. It is the first step in his macroscopic fluctuation theory development. It is just derives the hydrodynamic limits, but then we would like to understand the large deviations. Just one word about the fact that in fact these questions. So the motivation, also some other motivation to study this system is that in the case where you take some chains of oscillators. So where you have only local interactions, so it appears that the system, heuristically at least, they are described by in some cases, in the case where the potential of interaction is even, are described by fractional Laplacian. So fractional Laplacian, even if you have local interaction in your microscopic system. And so these models, this exclusion process, for example, could play the role of a toy model to understand also the macroscopic properties of its chains of oscillators. But just now, since I don't have so much time, I would like to finish by presenting some second kind of result that we obtain for some other interacting particle system, which is boundary-driven, which is a boundary-driven symmetric long jumps zero range process. So it is again some process with long jumps. So the picture is the following. So probably many of you know this system. So you have, again, now the difference with the exclusion process is that on each side you can have some arbitrary number of particles, and the particle will jump from side to side with a rate which depends on two parameters. So where is it written? Yes, it is written here. You see the rate to jump from x to y is provided by pxy, where pxy is just so p of y minus x, which is where the p is still heavy tail, but it depends only on some the number of particles that you have on the side x, g of k, where g of k is some given function, which has to satisfy some property, but anyway. And we assume that you have some symmetric exclusion process. So you have this relation which is satisfied, so that we can compute the equilibrium measure of the system. And we attach again the system with some reservoirs at each boundaries in order to fix the density, and the intensity of this reservoir are regulated by this kappa divided by n power theta. So there is some function which is a partition function, which will appear several times afterwards, which is this z of phi, which is defined by the sum over phi k divided by gk factorial. And so in this case, in this zero range process with long jumps, we know that we have some, if the two density as the reservoirs are the same, then the product measure with some given marginal that I will present just afterwards are invariant, But in fact, it turns out that even when you are outside of equilibrium, you have some environment measure which is product, which is a big difference with the exclusion process. In the exclusion process, we don't know what is the non-equilibrium stationary state in the case where the densities are different. But in the range process, even with these long jumps, we know that the environment measure will be product. And so it's the reason for which we can expect to have more information about the non-equilibrium stationary state, even if a priori this system is more complicated than the exclusion process, because if from the hydrodynamic limits point of view, we expect that the hydrodynamic limits are described by some nonlinear fractional equation. But the NESS will be quite simple. So as I told you, in the case where even if the densities are different, you have some product measures. And so here I wrote the stationary state. If you look at the endpoint correlation function, okay, now the probability is that on site 1 you have k1 particle, on site n you have kn particles, so it is a product, and the product with these marginals which are given by this formula, where phi n is some function. Okay, but this function there exists some function which is solution of some linear equations, but a linear equation of size at size n, so you cannot solve it explicitly. Okay, but you know it is product. You can prove it is product, and this phi n x is something to compute. And now there is some relation which is quite interesting, is that this phi n x, which is in fact the average of the g of xi x. Xi is represent as the configuration of the zero-range process. Okay, so xi of x is the number of particles of the zero-range process on site x, and so g is a function which is appearing in the rate to jump from site x to some site y. So this phi n x, which is appearing in this environment measure, is given by this quantity. But in fact, you can prove that it is also equal to the average in the stationary state, not the same stationary state, the stationary state of the exclusion process of the occupation number of the exclusion process. And so, since we have some hydrodynamic limits and some hydrostatics for the exclusion process, we can derive some hydrostatics for the zero-range process. So this is the theorem that one of the theorems that we prove is that the hydrostatic profile m bar of the boundary-driven zero-range process is given by this formula, where rho bar of u is the hydrostatic profile of the exclusion process. Okay, which can be with several boundary conditions, Neuman or Robin and so on, and it is a function, nonlinear function of this profile, which is provided by this function r of phi, which is related to the partition function. And okay, in fact, this m bar should be the solution, also the stationary solution of some nonlinear fractional diffusion equation with suitable boundary conditions. But here we don't need to have the hydrodynamic equation of the zero-range process, because we relate everything thanks to the information that we have on the exclusion process, which is easier to study from the point of view of the hydrodynamic limits and the hydrostatics. So this is the first problem, but in the case of the zero-range process, we can go further, and we can even obtain the non-equilibrium free energy that I was mentioning at the beginning. So it means that we can derive some large deviation principle for the non-equilibrium stationary state. So if we look at what is the probability here to see some profile for the zero-range process, which is equal to pi, where pi is some given profile, then it is exponentially small in the system size, and with some rate functional, which is f of pi, which is given by this formula, which is here. And in particular, this f of pi is vanishing on the typical profile of the hydrostatics of the zero-range process. And okay, so just to conclude, so here in the zero-range process, it is quite easy to derive some information about the non-equivalent stationary state. We have to pass through the information that we have on the exclusion process. But now, one thing which could be interesting is that a priori, if it's f of pi, we should be able to derive it by some macroscopic fluctuations theory framework, in which we first have to derive the dynamical large deviation functional of the empirical density of the zero-range process. And then by minimizing this rate functional over all the profiles going from minus infinity from the stationary profile and at time 0 to the profile pi, we should get this function. But okay, if you want to derive this dynamical large deviations problem, okay, first you have to understand the hydrodynamic limits. So in this case, they will be non-linear, but maybe it is not so difficult. But then if you look at the large deviations problems, so something which is not clear for me is that in these large deviations problems, what you do usually is that you want to observe some profile, so you have to perturb your dynamics in a suitable way in order that when you perturb the dynamics, you will observe this atypical profile for this perturbed dynamics. But what is the kind of perturbations that you have to put in the system is not so clear, and because the system is with a long jump, so a priori you could imagine that the perturbation is non-local. And so we try to do few things, but for the moment we have nothing very conclusive, and we'll be very happy if people will work on this problem of because I think there are many open problems in this direction, but establishing some large deviations problems for this kind of system with long jumps. Okay, so I think, yes, it is the last one. So thank you very much for your attention.
Thank you, Cédric. It was a very nice talk. So is there any question first in the online? Yes, I saw one. I think Pedro Cardoso has. So please, Pedro. Ah, no, it's okay, sorry. It was just to say congratulations. So is there any question?
I don't think that Pedro has so many questions.
No. He was saying congratulations. Okay. So is there any question? No, I can start with one. Just maybe to let people think. Ah, no, Milton maybe has. No.
Okay. So yes, I have a question. So Cédric, you mentioned this thing about the different definitions of the Laplacian operator, and actually the motivation for that first paper I wrote a long time ago about this thing was exactly that to understand what was the right definition of the Laplacian operators, at least in the context of our practical system. So it seems that almost more than 15 years after that, we still don't have an answer to that, no? Or you
yeah, but I think that it is very sensitive to the system. For example, if you take the system of oscillators, you know, the system of oscillators with this harmonic chain with some noise, then the operator that you get when you put the system in contact with its reservoirs is some spectral fractional Laplacian, which is not this regional fractional Laplacian that we have. So I would say it is a bit like, I don't know, it is, since it is long jumps, I think it is very sensitive to the boundaries. It is a bit like when you have this system with random masses, for example, harmonic chain with random masses. You see, you can have some Fourier's law in some, depending a bit of the boundary conditions that you have. So I think that it doesn't exist a single single answer to the question.
Okay.
In fact, I have a question related to this. So you expect that from exclusion processes or zero-range processes, the fractional Laplacian that you get will always be the regional one. You don't expect, so it's not possible to get another one.
But for the, okay, it depends on the reservoirs. Maybe because there are some other kind of reservoirs. For example, there is these reservoirs by the Masi, Presutti, and maybe with this one you can get some different Laplacian, fractional Laplacian. And I don't know, for the zero-range process, okay, zero-range process will be non-linear, but it will be related probably to the regional fractional. At least at the hydrostatic level, they are related. So I think that hydrodynamic levels will be related also.
Okay.
So,
okay. Thank you. So there is also a question from Sunder in the chat. He's asking, what is the type of zero-range rate considered in the last results? What are the conditions on G?
Okay, so the condition on G, so in fact, I have to say that, so we submitted the paper and then we had some answer of the referees, and now we were thinking about what are the exact conditions that we need. We don't need so much because in fact, we are considering only the system at with finite size. So in fact, we need almost nothing. We just need that the chain is irreducible and so on. But we don't need almost nothing. We don't consider the system in infinite volume.
Then I have a question or maybe a comment. So Cédric, yeah. So in order to get your hands on this quasi-potential, you need to solve this variational problem, and by solving this variational problem, you know that the trajectory which solves it, it's the hydrodynamic solution of the adjoint process.
Mm-hmm.
And for that, well, to write down this adjoint hydrodynamics, you need to guess what is the quasi-potential. So do you have, and well, usually how you guess your quasi-potential, you write down the Hamilton-Jacobi equation, and you propose a solution, and then you show that this solution it's indeed the correct one. So have you considered already this problem?
No, because okay, even in the nearest neighbor case, how can you find it if you don't have the solution of Derrida? So I mean,
the Hamilton-Jacobi equation, it's given to you, right? You have the Hamiltonian. You can write down the Hamilton-Jacobi equation, and then you can start guessing what should be the solution of this Hamilton-Jacobi equation.
Yeah, but first I need the quasi-potential. For the quasi-potential, I don't.
No, you don't need the quasi-potential. You just need the large deviation rate function of the dynamical.
No, yes, sorry. Yes, we need yes, exactly. But then even phase one, I don't have. I don't know what it is. Because okay. It is a problem that I mentioned. It's not easy for me to see what is the kind of perturbations that you have to consider in order to get this large deviation function, okay. This dynamical large deviation function. So it is the first step. Even before to ask to reply to your question, it is even in the case where you don't have any boundaries. See. There are some work. It was a long time ago. Some paper by Leonard and I don't know if what maybe Kipnis. No, I think it was Leonard alone, where they were deriving this large deviation function for the case of independent particle system. And but then you have some problem of convexity and so on. it is not as nice as the large deviation functions that were for diffusive systems. So I don't know.
Thanks.
Okay, thank you. Any other question? Okay, I don't see anyone.
No, there is
No,
a
yes,
question in
yes,
the
yes.
chat,
There
yeah.
is one question. Yes. So, from Federico, does the non-smoothness of the hydrostatic profile emerge only in the Dirichlet regime? Is this correct?
No, it emerges. It's also in the Robbins case also, and in the Neumann. No, not in the Neumann. Okay, in the Neumann case, the stationary profile is just flat. But in the Dirichlet and the Robbins case, Robbins boundary condition, it appears. Yes. But in PDEs, they don't know. They don't have any idea how to. Okay, I don't know. Maybe they were not so interested in this problem, but the people, very strong people, we asked the questions. They didn't know. They didn't have any answer. So.
Okay. Last chance for a question. Okay, it seems okay. Okay, so thank you very much, Cédric.
Okay, thank you to everybody.
Yeah, see you soon. Bye.
Bye-bye.